Good afternoon, everyone. How are we doing? Questions while we wait for others to come in? Come on in, everyone. We're up to 42. We'll wait a bit. Good afternoon, everyone. We seem to be stuck at 42. Absolutely. Absolutely. Business applications will be an essential part of the course. You should be doing all the odd questions in the textbook. I won't be assigning any one specifically. You should do them all. That way you'll get an understanding of the material and you should do extremely well in the course. The tutorials will start next week. The TA will post the pertinent information on my courses. Good afternoon, everyone. Come on in. All the information can be gotten on Minerva as far as when, the day and time for the tutorials. I don't know it by heart. So somebody's pointing out that the web work is still not working. They got it working, I believe, today. I've posted a link. Give it another 24 hours. Give it another 24 hours because it has to update via the My Courses class list. It does that once every 24 hours. I'm not sure exactly when. So Sophie is telling us that it's working today. Well then, very well. Okay, so that means it has updated. Thank you for the update. So WebWork should work fine now. Again, only assignment 0 is there. It's not for marks, but a tutorial on the WebWork system. If you're already familiar with it, you don't need to do it. Nandini is asking if the content in this class is easier than 133. I would say that 133 is probably 10 times harder than this course. You will have unlimited attempts for the web work. Shall we get started then? We'll do a quick recap of what we were doing last time. And well, there is no web work yet. So no due date yet. First assignment isn't even up. So last time we suggested that we were going to look at systems of equations. And let's take an example. Right, we have a system of equations, and I'm quite certain that all of you know how to solve this, right? You can isolate for one variable, perhaps x is 6 minus y, plug that into this one to get 6 minus y minus 2y is equal to 3. So minus 3y, and if you bring the 6 to the other side, minus 3y is equal to minus 3, or y is equal to 1. And if y is equal to 1, then x is equal to 5. Right? And 5 plus 1 is 6. 5 minus 2 is 3. The solution satisfies both equations. Isabel, the WebWorks 0 is just a tutorial for the WebWorks system. Click on every individual questions and you'll see that you have questions to answer, and you can answer directly on the computer. And then you submit your answer, and it gives you instant feedback as to whether it's right or wrong. It's not for marks, it's just a tutorial on the WebWorks system itself. If you have questions, you can email me. Very well. So, this is the usual way you know how to do in high school. An alternate approach that we saw last time was you could add or subtract equations. If we subtract the second equation, x minus x, these disappear. Y minus, right, so x minus x, that's 0. Y minus negative 2y, or y plus 2y is 3y. And 6 minus 3 is 3. So you get 3y is equal to 3, or y is equal to 1. Right? And combined, right, again, if you finish that up, we have just seen that y is equal to 1. And now if you subtract this minus that, so x minus 0 is just x, y minus y is 0, and 6 minus 1 is 5. In other words, x is equal to 5. We get the same solution as before. So we know it's correct. We're going to take this approach one step further, and instead of carrying around the x's and the y's, we're going to arrange these in an array called a matrix. Reserving the first column for the x's, the second column for the y's, and the third column for the constants. So our first equation here, x plus y equals 6, or 1x plus 1y is equal to 6. And the second equation, x minus 2y is equal to 3, or 1x minus 2y is equal to 3. And then we're going to do some operations on this matrix corresponding to what we were doing here. In other words, operations which don't affect the solution. What can we do to a system of equations which will not affect the solution? Well, here we were adding or subtracting a multiple of one row from another. If you multiply an equation by a non-zero number, you can always undo it, so it doesn't affect the solution. And if you interchange two equations or interchange two rows, this does not affect the solution either. So these are the three allowable row operations that we're going to perform in the hopes of finding the solution. Notice, what did we do originally? We subtracted the two. Let's do it. Row 2 minus row 1 for row 2. The new row 2 is going to be row 2 minus row 1. And you know, I know a lot of people have tried these row operations over the weekend, and as well you should. But you know, be careful. Be careful, because some of you are picking up a bad habit. So here's the good habit to pick up. You want to start with the row that's going to change. If you're adding a multiple of one row to another, start with the row that's going to change. So row 2 is going to change. So row 2, and now you add a multiple of another row to that. So row 2 minus row 1 for row 2. Some people want to do row 1 minus row 2 for row 2. Stay away from that. It's going to cause some issues later on. So row 2 minus row 1 for row 2 is what we want to do. This leaves row 1 unchanged. And the new row 2 is row 2 minus row 1. So this minus this, 1 minus 1 is 0. This minus this, minus 2 minus 1 is minus 3. And this minus this, 3 minus 6 is minus 3. Let's multiply this whole equation, right? This is very similar to this here, where we had 3y is equal to 3, right? This is minus 3y is equal to minus 3. What did we do? We divided by 3, or equivalently multiplied by 1/3. Let's multiply here by negative 1/3. Negative 1/3 row 2 for row 2. If we multiply row 2 by negative 1/3, first of all, that does not affect the first row. And what becomes of the second row? Minus 3 times negative 1/3 is 1. Minus 3 times negative 1/3 is 1. If you take a step back, remembering that the first column is for the x's, second column for the y's, and third column for the constants, this last row here is telling us that 0x plus 1y equal to 1. Or y is equal to 1. Exactly what we had here. Let's finish it up. What happened next? We subtracted row 2 from row 1. Let's do it. Let's do it. Let's say row 1 minus row 2 for row 1. What does that give us? This minus this. That's a 1. This minus this, 1 minus 1 is 0. This minus this, 6 minus 1 is 5. Second row remains unchanged. And there you have it. If we take a step back, again, remembering that this is x, y, and equals. This first row is telling us that 1x plus 0y is equal to 5, or x is equal to 5. The second row is telling us y equals 1. Exactly the solution we had found originally. Joseph is asking if it's acceptable to write the progression of the matrix horizontally instead of vertically. Absolutely, right? Sometimes you know that you only have 2 or 3 row operations to do, and they can all fit on the same line. Go ahead and do it. Nothing wrong with that. Sophie is asking, what is the best order to achieve the goal answer, right? I mean, are we looking, well, so perhaps I'm reading too much into that. First of all, are we looking for the 1001, right? I mean, so some people had asked the question, what about 0110 and some stuff, right? That could have been allowable as well. We suggested that we were going to stay away from that, and the reason for that will be clear today. But perhaps Sophie was asking the best order to get to that step. And here's what I like to do. I like to start with a 1 in the upper left-hand corner, if at all possible. Use that 1 to clear out the column. Then get a 1 in the next position and use that 1 to clear out the column. Luca is asking if we'll be assigned pages. Well, I mean, here we did an example that I came up with, but as you know from last week, I like to do a lot of examples from the book. So let's do that. It's taken from page 57. Right, taken from page 57. We'll do some examples from this page and possibly other pages as well. Be on the lookout for that. What you need to do after this lecture is go home or wherever you are and do lots of exercises from those pages. Do all the odd questions from those pages. You cannot do too many. Julia is asking if I suggest that you solve the equations without matrices. I do not. Don't do it. There's no point in doing that. Go straight to matrices. Solve using matrices. And then you can check if your answer is correct. You don't need to look in the back of the book. You can take a moment and plug those in to the system of equations. Does your solution satisfy the system of equations? Now, don't let the S and T fool you here, right? It's 2 equations, 2 unknowns. We're going to set up a matrix with the first column reserved for the S's, the second column reserved for the T's, and the last column reserved for the constants. So 12S plus 5t is equal to 9. So this is s, t, and the constants. 12s plus negative 5t is equal to 9. Second equation, 3s minus 8t is equal to negative 18. There it is. Now, you know, right? I mean, my suggestion was, if at all possible, to get a 1 in the upper left-hand corner. Well, I mean, you have some approaches, and first of all, it doesn't, this is not a strict requirement, but you have some options here. Some people like to divide, right? If you divide the equation by 12, divide the first row by 12, or multiply by 1 over 12, you're going to get that required 1. But that introduces fractions. And nobody likes to add fractions. If you can leave those, that's very nice. Here we have a 3 and 12. So what I would do, I would say row 1 minus 4 row 2 for row 1. And that would change the 12 into a 0. What do we get? This minus 4 times that, 12 minus 12 is 0. Right, it's the row 1 that's changing. I'm starting with the row to change. Minus 4 row 2 for row 1. This minus 4 times this. So minus 4 times that gives me 32. Positive 32 minus 5 is going to be 27. And 9 plus 4 times 18, it's 80 minus 8, so 72. 72 plus 9, 81. All right. Now I might want to interchange row 1 and row 2. Also, 27 and 81. Maybe we want to change this into a 1. Do we want to do 2 operations at once? I mean, we were doing that before. So let's do it. Let's change this into a 1. 1 over 27 row 1 for row 1. And then let's interchange. Thank you, Annabelle. And then let's interchange row 1 and row 2. So row 1 interchange with row 2 after having divided row 1 by 27. What does that give us? This is the new row 1. So 8 minus 3, 3 minus 8 minus 18. And second row becomes, you tell me, 0, 1, and, does everybody see it? 0, 1, and 3. Thank you. Let's use this 1 to get rid of that 8. Row 1 plus 8 row 2 for row 1. Scott, interesting. Let's not do that. Let's not do that. Let's not do that because again, you might run into problems later on. So while I don't mind doing 2 operations at once, let's not describe them as you did. There was a question from Ed. I did not, about losing marks, I did not realize there was a question. How would we lose marks for writing too many steps? No, of course not. Of course, you're not going to lose any marks for writing too many steps. So here we go. So 3 plus 8 times 0, that's still a 3. Minus 8 plus 8 is 0. And minus 18 plus 24 is a positive 6. Let's finish it up by changing this into a 1. 1/3 row 1 for row 1. And you see the beauty of having waited until the end. So 1/3 times 3 is 1, 1/3 times 0 is 0, and 1/3 times 6 is 2. The beauty is that at no point did we introduce fractions. We waited until the complete end. No fractions. Here, S is equal to 2, right? First equation. And second equation, T equals 3. Let's check. Is this correct? 24 minus 15 is 9. 6 minus 24 is negative 18. Perfect. There it is. You know it's right. It satisfies the equations. Right? If you had divided by 12 or divided by 3 to get the 1 as a first step, you would have had to deal with fractions throughout the whole row reduction process. Britton is asking if we can do something like 4 row 2 minus row 1 for row 2. As I'm suggesting, you want to stay away from that, right? If you're changing row 2, you want this to be a row 2 as well. And while it's not clear why you want to stay away from something like this, it'll be clear a bit later on. As was asking us to do question 16. I don't think I wrote it down. Can you give it to us? Can you give us the equations involved in 16? We can do it. Three x plus 5y plus 2. And 9x plus 15y plus 6. Thank you. All right, so first of all, let's rewrite this appropriately by bringing the 2 and the 6 to the other side. Right, so in other words, we have 3x plus 5y is equal to minus 2, and 9x plus 15y is equal to minus 6. Right, so we're bringing the constants to the other side. And now let's set up a matrix. Set up a matrix where we will reserve the first column for the x's, second column for the y's, third column for the constants. And now let's use this 3 to get rid of that 9. Again, let's somebody's suggesting taking 1/3 of row 2 for row 2. Nothing wrong with that. But then I claim you're just going to subtract the 2 anyway, so might as well do that in one step. Row 2 minus 3 row 1. Row 2 minus 3 row 1 for row 2. And then what happens then? Well, first row remains unchanged. But second row, what does the second row become? 9 minus 3 times 3, that's 0. 15 minus 3 times 5, that's 0. And minus 6 plus 6, that's 0 as well. So we get a row of zeros here. So where are we going with this? Well, no matter what you do now, I think it should be pretty clear that this is never going to reduce to something that looks like this. Right? So you'll never be able to bring this matrix into the 1, 0, 0, 1 scenario, which now opens up a whole new can of worms. If 1, 0, 0, 1 is not the ultimate goal, what is the ultimate goal? Before we answer that question, let's do one more example. And then we'll discuss, we'll come back to this example. But before we do so, let's do one more. All right, let's consider this. One more example before we go back to that. Let's put everything into a matrix, reserving the first column for the A's, second column for the B's, and third for the constants. And now let's use this 1 to get rid of that 3. Row 1 minus 3 row 2 for row 1. And then maybe bring, right, since you're going to have that 1 now, maybe bring it up, interchanging the 2 rows. Can we do these 2 steps at once? So this will become my new row 1. And the row 2 is this minus 3 times that. So 3 minus 3 is 0. The minus 8 plus 6 is minus 2. And 14 minus 6 is 8. Now we have a minus 2 and a minus 2 here. So that's nice. Let's make use of that to get rid. Row 1 minus row 2 for row 1. And then change this into a 1 by saying negative 1/2 row 2 for row 2. What does that leave us with? 1, 0, minus 6, 0, 1, minus 4. Excellent. Excellent. Now let's check. Is this correct? Minus 18 plus 32 is 14. Minus 6 plus 8 is 2. Very nice. Very nice indeed. Can we do 3 variables? We can. Let's not for now. We'll do a few examples in 3 variables in a moment. But now I think the question we need to address is, if not all matrices can be brought into the 1, 0, 0, 1 situation, what is the goal? What is the simplest form a matrix can have once you row reduce? When do you know how to stop row reducing? And to that end, let's take an example. An example very similar to the one we looked at. Consider this system of equations. Well, in fact, let's consider this one first. Let's rewrite again everything into a matrix and row reduce. See what happens. So we'll reserve the first column for the x's, second column for the y's, third column for the constants, right? So 1x plus 1y is equal to 1. And 2x plus 2y is equal to 3. Yeah, Nandini has given us the answer here. We'll see. We'll see that occurring. Absolutely. Right? You all see what's going to happen, right? Let's use this one to get rid of that 2 by saying row 2 minus 2 row 1 for row 2. So the first row remains unchanged. 2 minus 2 is 0. 2 minus 2 is 0. And 3 minus 2 is 1. If you look at the last row, what is the last row telling us? Right, again, remember we had reserved the first column for the x's, second column for the y's, third for the constants. This last row here is telling us 0x plus 0y is equal to 1. In other words, 0 is equal to 1. You know this is nonsense. 0 is not equal to 1. So this is inconsistent. The system is inconsistent and there are no solutions. The system is inconsistent. There are no solutions. Leon is asking, how did we know that there would be no solutions without working it out? Consider this. You see that this 2x plus 2y is the same as this, just multiplied by 2. So for the system to be consistent, if you're multiplying the left side by 2, the right side better be multiplied by 2 as well. So instead of having a 3, it should have been a 2. It isn't, we're in trouble. What if we did have a 2? What then? What would have changed? What would have been the solution? Right? What if it was a 2? Let's see what happens. Right? Let's put again everything into a system of equations. See what happens. An array, a matrix. See what happens. 2x plus 2y is equal to 2. And let's do exactly what we did. Let's use this one to get rid of that 2. Row 2 minus 2 row 1 for row 2. Right? First row remains unchanged. Second row, 2 minus 2. 2 minus 2 times 1. 2 minus 2 times 1. Take a step back and look at what the last row is telling us. This last row is telling us that 0x plus 0y is equal to 0. So this last row here is telling us 0 is equal to 0. At least it's not inconsistent. Right? At least it's not inconsistent. Here we had 0 is equal to 1, which you know not to be true. Here 0 equals 0, well, you know that. Nothing wrong here. But what? But now if you take a step back, you'll understand that no matter what row operations you do, you're never going to bring this into the 1, 0, 0, 1 business. Right? There's nothing you can do here. There are no row operations you can do to introduce a 1 in this spot without changing this. So this is not going to row reduce to this. In fact, this is the simplest form this matrix can achieve. Which brings up the question, how do you know? How do you know when to stop? What is the simplest form the matrix can have? What do this matrix and this one have in common? Definition. A matrix is said to be in reduced row echelon form. So a matrix is said to be in reduced row echelon form, RREF for short, if it satisfies the following conditions. Right, so our attempt now is to make a connection between this and that and all the other matrices that you cannot row reduce to this. Leon, what you're saying is correct, but there are other situations. I mean, it's not only those two. As we'll see shortly. So a matrix is said to be in reduced row echelon form if it satisfies the following conditions. Number one, the first non-zero entry in each row is a 1. Called the leading one. So the first non-zero entry in each row is 1. This is called the leading one, right? So first non-zero entry in the row, first non-zero entry in the row, first non-zero entry in the row. These are known as leading ones. Cassia, you're correct, that there are infinitely many solutions. We did not mention that yet. We'll come back to that momentarily. But first, I want us to understand the simplest form the matrix can have. Your goal in row reduction is reduced row echelon form. What does reduced row echelon form mean? There are 4 conditions. The first one, first non-zero entry in each row is a 1, called the leading one. The leading ones are the only non-zero entry, non-zero, in their column. Number 3, the leading ones move to the right. As you go down the matrix. And 4 rows of zeros. If any, are at the bottom. Let me give you a moment to take that down. How are you doing here? Reduced row echelon form. Well, Shirley is slightly confused here. Let's take a few examples. the process, as Namdini suggests, the process of bringing a matrix into reduced row echelon form is known as Gaussian elimination, right? The row operations that we're doing, it has a name, it's called Gaussian elimination. And as was asking, if we switch row 1 and row 2, how does the last point matter? Well, right, I mean, it doesn't. It just says that you want to bring the row of zeros at the bottom, which you can do by switching rows. So this is reduced row echelon form. Let's take an example. Right, I mean, we've been row reducing stuff. We had -4 and -2, I think, or -4 and -6, whatever, right? I claim that this thing before the equals here is in reduced row echelon form. Let's convince ourselves. The first non-zero entry in each row is a 1, called the leading 1. The leading 1 is the only non-zero entry in its column. Right? Here we have a 0. The other entry in this column is a 0. As you go down the matrix, the leading 1s move to the right. This is to the right of that one. Rows of zeros, if any, are at the bottom. Well, you don't have any rows of zeros here. So this fourth condition is superfluous. There it is. This is in reduced row echelon form. The 1, 0, 0, 1, as you would imagine, because that was our goal originally, this is reduced row echelon form. But let's take the example we just looked at, the 1, 1, 1, 0, 0, 0. First non-zero entry in each row is a 1. Here you don't have any non-zero entries. So the first non-zero entry in each row is a 1, called the leading 1. The leading 1 is the only non-zero entry in this column. Looking good. Leading 1s move to the right as you go down the matrix. Well, there's only one leading 1. So that condition is vacuous. And rows of zeros, if any, are at the bottom. There it is. This is in reduced row echelon form. Consider this, which we were saying last time, right? I mean, you could have worked towards that, and then you could have simply read off the answer as well, but this is not in reduced row echelon form. Right? Let's understand why that is. The first non-zero entry in each row is a 1, called the leading 1. That's correct. The leading 1 is the only non-zero entry in its column. That's correct. Leading 1s move to the right as you go down the matrix. Well, that condition is not met. That condition is not met. Condition 3 fails here. But you can bring it to reduced row echelon form by just interchanging row 1 and row 2. There it is. Reduced row echelon form is the simplest form the matrix can have. Right, so then the obvious question arises. If this is the simplest form the matrix can have, if this is the end goal in row reduction, we should be able to read off the solution. What is the solution here? what is the solution. So what we're going to do to come up with a solution is look at all the variables. Right, first of all, this was x, this was y, and equals. We're going to look at all the variables that don't have leading ones. X has a leading one, but y does not have a leading one. We're going to replace y with a parameter. So y gets replaced with a parameter, y equals t. And then the first equation here was x plus y is equal to 1. So x is really 1 minus y, but y is t, so x is 1 minus t. And this is the solution for any real number t. You have infinitely many solutions. You can verify, right? If you remember the system of equations that led to this, we had x plus y equals 1, and 2x plus 2y is equal to 2. You can verify that this satisfies, right? If you plug in, x is 1 minus t. So 1 minus t plus t, right? X plus y. You see that the t's cancel and you get 1. And then 2x plus 2y, what is that? This is 2 minus 2t plus 2t, and that's just 2. It satisfies both equations. And there you go. I know what you're thinking. You don't have to learn anything, and you're not going to use matrices. It's a terrible approach. Terrible approach. You have to learn matrices. You have to learn row reduction, and not only that, you have to be an expert in row reduction this week. So drop everything you're doing and make sure that you master row reduction immediately, because everything is going to depend from now on. Everything is going to depend on how good you are with row reduction. Everything is going to depend on how good you are with row reduction. And let me tell you that the midterm is not the place where you want to learn row reduction. If you don't know how to row reduce by the midterm, things are not going to go well. I guarantee it. You cannot just keep the y. You want to replace y with a parameter. So all the variables that don't have a leading one get replaced with parameters. So let's go back to 16. I forget what 16 was. Somebody let me scroll back up here. We had it. 16. 3x plus 5y was was minus 2, and then we had 9x plus 15y was minus 6. Let's go back to this. Go back to this. We had set up our matrix 3, 5 minus 2, 9, 15 minus 6, and we had used that 3 to get rid of the 9. Row 2 minus 3, row 1 for row 2. So first row remains unchanged. Second row, 9 minus 3 times 3. 9 minus 9 is 0. 15 minus 15 is 0. Minus 6 plus 6 is 0. Here's my question to you. Are we done? Is this in reduced row echelon form? Is this the simplest form the matrix can have? Or must we continue? The answer is no, thank you. What's left? What need we do? There's no leading one, thank you. So first non-zero entry in each row should be 1. So let's change this into 1. 1/3 row 1 for row 1. What becomes of this? We get a 1 here, 5/3, and minus 2/3, and a row of zeros. Is this in reduced row echelon form? Are we done row reducing? Let's go through the conditions. The first non-zero entry in each row is a 1, called the leading 1. That condition is met. The leading 1 is the only non-zero entry in its column. That condition is met. Leading 1s move to the right as you go down the matrix. There's no other leading 1, so that statement is vacuous. Rows of zeros are at the bottom. All conditions are met. This is in reduced row echelon form. We should be able to read off the solution. What is the solution? Right, remember, this is a column for the x's, this is a column for the y's. The y's don't have a leading 1. Y gets replaced with a parameter. Y equals t. The first equation was saying x plus 5/3y is equal to minus 2/3, or x is minus 2/3 minus 5/3y. So if y is t, x is minus 2/3 minus 5/3t. And there it is. Is this correct? Is this the right answer? It should satisfy both equations. Check. What is 3x plus 5y? X is this. Well, minus 2/3 minus 5/3t plus 5y, y is t. Distribute, you get a minus 2 minus 5t plus 5t. The 5t's cancel out, leaving you with a minus 2. Exactly as suggested. If we do the other one, 9x plus 15y, x is again then y is t. Distribute, we get a 9 and 3 cancel, leaving me with a 3 times a minus 2 is minus 6. 9 divided by 3 is 3, so minus 15t plus the 15t, these cancel out exactly as you would expect, right? Leaving you with a minus 6, exactly as predicted. Why does t need to substitute y? Because at some point, right, look, I mean, we're introducing this in a very simple case, 2 equations, 2 unknowns. But immediately, right now, we're going to do an equation 3. We're going to do an example where we have 3 equations, 3 unknowns. And you know this scales up. 4 equations, 4 unknowns, 5 equations, so on and so on. So we need a methodology to be able to describe everything. This is taken from page 70. So what did we prove at the end by finding minus 2 and minus 6? We proved that 3x plus 5y is equal to minus 2. That was the first original equation in the system. And the second equation was 9x plus 15y equal to minus 6. We proved that this was a solution to these system of equations. We proved that this is the right answer. So you don't have to look in the back of the book to check. You can check immediately. On an exam, you could check immediately. And you should. Consider this. I'll give you a minute to set up the equation, set up the matrix. Right, 3 equations, 3 unknowns. How do we apply these matrices to vectors? We're not going to do any vectors in this course. So set this up. You know what to do. We'll reserve the first column for the x's, second column for the y's, third column for the z's, and fourth column for the constants. So 1x plus 0y is equal to minus 3. 0x plus 1y plus 1z is equal to 9. And minus 2x plus 3y plus 5z is equal to 33. Is it lagging? It happens sometimes after an hour. We'll wait. Let me know when you're back. Is it okay for everyone, or is there a lag? It's fine now. Thank you. We're back. Everybody's back. Excellent. All right. So there you go. I mean, we have this. We have this matrix, which we want to reduce to echelon form. So we have a 1 in the upper left-hand corner. That's nice. Let's use that 1 to get rid of that 2. Row 3 plus 2 row 1. So first row remains unchanged. Second row remains unchanged. Minus 2 plus 2 is 0. 3 plus 0 is 3. 5 minus 2 is 3. 33 minus 6 is 27. We have a 1 here. Let's use that 1 to get rid of that 3. Row 3 minus 3 row 2. One-third row of 3 for row 3. You could do that. That's fine too. I claim this is going to be a bit faster. Zero minus 0. 3 minus 3. 3 minus 3. 27 minus 27. How are we doing? What's my next row operation? What's next? Anyone? You tell me. Well, perhaps we should ask ourselves, is this in reduced to echelon form? Perhaps we're done. And if it isn't in reduced to echelon form, then that will kind of tell us what needs to be done. So let's ask the question, is this in reduced to echelon form? What is reduced to echelon form? The first non-zero entry in each row should be a 1. Called the leading 1. The leading 1s are the only non-zero entry in their columns. So you see, here we have a leading 1, and the rest are zeros in that column. Here we have a leading 1, and the rest are zeros. So that condition is met as well. First two conditions are met. The leading 1s move to the right as you go down the matrix. Well, that's correct as well. This is to the right of that one. And last condition, rows of zeros, if any, are at the bottom. This is in reduced row echelon form. This is the simplest form the matrix can have. I know some of you wanted to use that one to get rid of this, right? By adding row 1 plus row 2 for row 1. But if you do that, you're going to get a 0 here, but you're going to change this 0 into a 1. This is in reduced row echelon form. Nothing you do will make it simpler. This is the simplest form the matrix can have. So this is it. This is in reduced row echelon form. We should be able to read off the solution. What is the solution? X has a leading 1. Y has a leading 1. Z does not have a leading 1. We replace Z with a parameter. Britton is asking, does it satisfy that the leading ones are the only non-zero entry in their column? And it's done. Very well. So this first equation, this first row, what was that first row saying? That first row was saying 1x minus 1z is equal to minus 3. Or x is equal to minus 3 plus z. But if z is t, then x is minus 3 plus t. And similarly, the second row was saying at y plus z is equal to 9. Or y is 9 minus z. But if z is t, y is 9 minus t. And this is the solution for any real value of t. So again, you see you get infinitely many solutions. When t is 0, you get a solution. When t is 1, when t is pi, when t is 1 over root 2, you get a solution, and so on and so on. You get infinitely many solutions. Shall we verify? This solution has to satisfy all 3 equations. Let's just do one of them. But if you do x minus z, what is x minus z? It's minus 3 plus t. That's the x part. Minus t. The t's cancel, and you're left with minus 3, exactly as expected. The solution still has to satisfy the other 2, right? You need to check all 3, because it is possible that a mistake has been made. And it is possible that it satisfies just the first one, or even the first 2, but fails for the third. So you really need to, if you want to check, you have to check that it satisfies all 3. I'll leave that to you. Do we have time for one more? Do we have time for one more? All right, one more. We'll end with this one. Set up your matrix. And row reduce. You know what to do. We already have 1 in the upper left-hand corner. We'll use that to clear out the column. Let's do 2 operations at once. Row 2 plus 2 row 1 for row 2. Row 3 minus 3 row 1 for row 3. So this plus 2 times that, 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 this minus 3 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 times that. Is that correct? Let me use this minus 1 to get rid of that minus 1. By saying row 3 minus row 2 for row 3. And then maybe changing that to a positive 1 by saying negative row 2 for row 2. And for those of you who were saying that this is easy, you're right, it's very easy. But this is how good you have to be. You know that you've mastered row reduction when there is absolutely no hesitation as to what the next steps are. This is where you need to be. And not in a month by the end of the weekend. You have 1 week starting today to master row reduction. It's not 25 at the bottom. 25, yes, thank you. I was thinking 25 and then row 21. Absolutely, thank you. So this minus that is 37, and this minus that is 0. We still need to do a bit more before I release web work 1, maybe by the end of the week, if we've done enough. Let's change this into a 1. 1 over 37, row 3 for row 3. So that'll change this into a 1 and this into a 0. So, well, I mean, okay. I'm very tempted to do a few operations here, but let me not do it so that I don't lose anyone. Now that I have 1 here, let me use that leading 1 to clear out the column. Row 1 plus 7, row 3 for row 1. Row 2 minus 12, row 3 for row 2. And finally, row 1 minus 2 row 2 for row 1. So this minus 2, so minus 8. And let me just look back at the equations we had. X plus 2y minus 7z is equal to minus 2. And we had 2 more equations, but I just want to see if it satisfies at least the first one. Minus 8 plus 6 is minus 2, plus 0 is minus 2. At least it satisfies the first equation. I'll let you check that it satisfies the other 2 as well. How are we doing here? Questions? So like I said, you have to be an expert in row reduction. As good as I am, as fast as I am, knowing exactly what needs to be done from now on at every step of the way in your row reduction process, you need to know what to do. Questions? So a good place to end then. We were doing stuff from page 57 earlier, and then page 70 as well. So do all of them. Do all the odd questions. There are some word problems that we did not attend yet, especially related to business. Go ahead and do those as well. I mean, in the beginning, you have to introduce variables. I mean, you're buying 2 bags of wheat and 3 bags of potatoes or something. So, I mean, it's not difficult stuff that you first translate into equations, introducing variables, and then you'll have a system of equations. So all we've been doing are systems of equations. Go ahead and do those. Practice, practice, practice. We'll pick this up again on Thursday. Thank you all for coming, and I will see you then.